All right, so now we got two statements. There are two ways you can induce current. You can change the strength of the magnetic field inside a constant area, or you can just vary the area exposed to the magnetic field. That's also going to induce current. Guys, stating a simple concept using two different concepts is not the way we do stuff. In physics, we always look for the most simple explanation possible. So what we will do is we will take these two concepts and unify it into a single statement by using the concept of flux. Okay, so what's flux? Flux is the same concept as before. Flux means flow, right? In this case, what's flowing is the magnetism through this area. All right, so that's the amount of magnetism intercepted by the area of the loop. That's what it means. All right, so that's the amount of magnetism that's going to flow through the area of the loop. So two concepts are combined into one. So what happens if you just vary the strength of the magnetic field inside this area? All right, it's going to change the flux. So if you change the flux, any variation of flux is going to induce current. All right, so there are two ways you can vary the flux. You can either vary the strength of the magnetic field inside the area, inside the loop. That's one way you can actually induce current. The second way you could do it is just take the area and then vary the area exposed to the magnetic field by either spinning it or just moving it side to side, just like that. That's also going to change flux. All right, so summary statement is any variation of flux is going to induce current. Any variation of flux will induce current. That's it. This becomes the Faraday's law. So the Faraday's law, simply put, is any variation of flux will induce current. And then we also came up with a mathematical expression for it. So any variation of flux will induce current. Okay, I'll let you know it's 22, 31 derivations. Okay, it's fine. Okay, so open up the lecture review material. So AC versus DC. AC, the direction of the current is alternating. DC, the direction of current is constant. AC is generated using magnets. DC is generated by using a battery. All right, the order is, I'm not going to follow the same order. All right, I'm going to start at 5. So what's flux? In this case, the flux is flow. What's flowing is the magnetic field through the area of the loop that you're looking at, current loop. So that's the magnetism flowing through the area of the current loop. Magnetism intercepted by the area of the current loop is going to be our flux. That's it. All right, so what is the Faraday's law? Simply put, it says if you vary the strength of the magnetic field within that loop, any variation of the strength of the magnetic field within the loop is going to induce current. That's what it means. So how do you vary the strength of the, how do you vary the flux? There are two ways you can vary flux. One way of doing it is keep the area the same, change the strength of the magnetic field. All right. The second way you could do it is, you can change the flux. The second way of doing it is keep the magnetic field the same. Just change the area which is exposed to the magnetic field. All right, so there are two ways of doing it. All right, so now let's go back and rewrite everything. So flux is the amount of magnetism which is going to be intercepted by the area of the loop. All right, so that's our flux. So what is the Faraday's law says? It says any variation of flux is going to induce current. Okay, guys, notice that I'm not using an equal sign. Okay, so that's a hint right there, which means that there's no equality here. All right, so the next question, does any variation of the size of the area exposed to the constant magnetic fields change the flux? Absolutely it would. So if you vary the area exposed to a constant magnetic field, it's certainly going to change the flux. Okay, now notice that this is an equation, and that in turn is going to induce current. All right, so the next statement is, this time we're varying the strength of the magnetic field within the area of our loop. So will that change flux? Absolutely. All right, so this time I'm varying the strength of the magnetic field within the area of the loop, and that's certainly going to, I messed it up. It's going to change flux, and that's going to induce current. All right, so that's it. All right, so 5, 4, 3, 2, that's the direction we will go. Okay, so now move on to number 6. Does the change in flux induce voltage or current? And why? All right, guys, I'm open to a discussion, real fast discussion right now, because this is, I think this may be
with current.
Okay, Alec, was it you? Okay, explain. Who said current? Ian, go ahead.
I did, yeah, because it's moving the electrons, it's creating current. There's never like a potential difference between them.
Okay, Ian, I'm gonna give you 5 points for saying the wrong thing. The only thing I like is you justified it well. because you're saying I don't see a potential difference, right? That's a really good point because you said you thought about voltage or potential at first, and then you said, hey, this is not attached to a battery. So obviously you're generating current without generating any sort of voltage, right? That's fine. Okay, so what do we know from the previous chapters? What causes charges to move in the same direction? Guys, what causes the charges to move in the same direction is the electric field. Acting on it is going to cause a force on it, and then it's going to get displaced in this direction. Force times displacement is going to be the energy, which means that the energy is going to be stored inside the electric field, blah, blah, blah. Oh, shit. By that vanishing argument, for you to have a current is always going to be caused by a voltage difference. So the current is always going to be related to the voltage difference. All right, so what causes current? Voltage does. You know, how do you generate voltage without a battery? That's where it kind of gets interesting. All right. And so let's skip back to the lecture notes. All right, so take my word for it at first because Ian has a valid point. Okay, so Ian says there's no battery, so how's that possible? So we'll just build on our previous experience. So what do we know? We know that the current is going to be caused by a voltage difference. All right, that's the Ohm's law that we've been discussing for a while. So what must happen is the change in flux must be inducing a voltage, and we know for a fact that voltage is what generates current. That's it. Okay, once again, there's an arrow. All right, so I'm saying that the change in flux is going to induce voltage, and voltage is what drives current. And then we will go, wait a minute, we will turn this into an equation only if I could do the following. I'm going to change notation at this point. Instead of using V, we will get to use the symbol epsilon. Okay, epsilon stands for EMF. EMF simply means electromotive force. I think we discussed that before. Okay, so they came up with the concept of electromotive force because they didn't have the concept of voltage or potential at the time. They figured that electricity was a fluid, and for it to move, it requires some kind of a force. And they figured that the charges would go from a state of excess to a state of deficiency. The state of excess was the positive state, the deficiency was negative state. So what's happening is obviously change in flux is creating an electric field inside the wire. The electric field acting on the charges, generating a force, and the charges are accelerating in the direction of the electric field. All right, so you end up getting this moving potential of voltage, which is known as electromotive force. Okay, let me check to see if that's symbolism at some point. Okay, so I end up changing symbols right here on the side page. So, which means that we end up getting this dynamic voltage or potential difference inside the line. Okay, so that's what it means. So change in flux generates some kind of a voltage difference, and the voltage is what drives current. All right, so going forward, let's go down to this portion of the equation. In reality, what happens is you end up putting a minus sign here, okay, denoting the direction of the current, which we'll discuss later. I don't know if it's going to happen today or next time, by the lens as well. So I'm not going to get into it right now. It's not that important, but it'll become important next time. Okay, so let's get back to Faraday. Okay, guys, imagine that you're changing the flux within a single loop of wire. So what happens? You end up generating a certain amount of current, right? You change the flux to one single loop, and you generate a certain amount of current. What happens if you actually double the loop, double the size? If you double the size, what happens? The amount of current that you generate is going to double. If you triple the loop, the amount of current that you generate is going to triple. If you add like 10 loops, the amount of current that you're going to generate is going to go up by 10 times. So all of a sudden, you notice that by increasing the number of turns, you can increase the voltage, you can increase the current. By reducing the number of turns, okay, let's back up. By reducing the number of turns, you can reduce the voltage and you can actually reduce the current. All right, so this is something that Faraday came up with, the guy who could not do mathematics. Now there's a way. You can generate as much current as you want. All right, the only thing you have to do is just control the number of turns, number of loops that you want to have inside your coil in this case. All right, let's back out of this. Let's get back to the lecture review materials. So does the change of flux induce voltage or current? All right, so what we know that the change of flux in this case is actually induced voltage, and the voltage is what drives current. All right, so how does changing the number of turns in a coil affect the induced voltage on the current? All right, so this is the flux, change in flux for a single coil. All right, so by increasing the number of turns, you can actually increase the voltage. In this case, we're using epsilon. And in doing so, you can also change the current. All right, so increase the number of turns, voltage goes up, the current goes up. Reduce the number of turns, voltage goes down, the current goes down. All right, so I'm going to put a negative sign here. Something that we will discuss later. All right, so Lenz's law. So what's the next question is, what is the Lenz's law? I don't care about that today. All right, that's not the most important stuff with the time being. All right, guys, just take a break for 10 to wrap it down 10. Okay, so moving forward. All right, guys, we've been generating current pretty much the same way ever since 1800s. I think ever since 1880s, more like it. Technology hasn't changed that much. The only thing you have to do is just get a coil of wire, and then just spin it inside a constant magnetic field. Normally, we would do it 60 times per second, which means that we keep varying the direction of the current 60 times per second. So that's the reason why it's called 60 hertz current. That's what we get from the wall socket. So the question is, how do you get to spin this thing 60 times per second? All right, notice that it's done mechanically, so you see a hand. So who can actually spin this coil 60 times per second? 60 times per second. How does that work out? How do we do that? I mean, even if you get a Canadian and then just give them tons of money, they're not going to be able to spin it 60 times per second, as crazy as they may be, guys. So how do we get to spin these coils 60 times per second? Any ideas?
2 Canadians.
What?
2 Canadians and like your train.
Well, if properly trained Canadians, 2 of them will do it. If it cannot be done by a single one. All right, so what do? We end up using gears, right? All right, so you got advanced gear systems or whatever. By the time you get down below to this level, to the level of a spinning coil, it's spinning 60 times per second. Okay, so the question is, how do you spin this thing mechanically? By what mechanical means do we get to spin the coil? All right, so I'm open to ideas at this point.
Maybe like a steam
Okay,
engine
steam.
or
Right.
a well or whatever. Doesn't really matter. A dam with turbines in it.
Okay, Nathan, I'm going to give you 10 points. So you got the pressurized steam. So how do you do that? Boil water, right? As the steam is going up, it's going to turn the turbine. So I'm going to give you 5 points for saying turbine is opposed to turbine. Turbine is a head gear. Turbine is the setup that you guys are looking at. All right. Another way of doing it, the running water, is you got to turn the turbine. Okay, so what else? Steam. How do you generate steam? You can do it using coal. What is the meaning of a nuclear power generator? How did that work?
It's just a big steam engine that uses nuclear reactors as a heat source.
All right, so give yourself 5 points for that one. Nuclear power generator is exactly, instead of using coal, you can use radioactive material to heat the water, right? It just turns into steam. That's it. All right, I used to say that that's one of the safest ways, one of the cheapest and safest ways of doing that. And then look what happened in Japan. And so evidently you can't get too cocky, so the safety is important. All right, so the whole idea of the nuclear power generation is just enough water to turn into steam. And then we talked about wind already. The whole idea is we spin this by mechanical means. So the mechanical energy is the one that turns into electrical energy. So by mechanical means, we spin the coil.